So let's go back to the generalized least squares problem, which is what? Well, we pose this model that y equals phi theta plus epsilon. So this is a vector, a random sample xi, yi. It's a vector of these yi's. We have this model yi is a linear combination of some basis functions which are contained in this vector of basis functions here. So this transpose theta plus epsilon I. So we collect all of these inside a vector, all of these inside a vector. We define what's called a design matrix, which is this thing here. The first row is this vector of basis functions at x1, down to the last row is that same vector of basis functions at xn. Right, so we can write the model compactly for the sample that we have, the random sample, as y is phi theta, design matrix times theta, plus this here. And so this is the model we assume in generalized least squares. We then assume, so Gauss-Markov assumes that the expected value of epsilon conditioned on all of the inputs or equivalently on this design matrix, which is a function, a random function of all these random inputs, is 0. So that's the Gauss-Markov assumption, the first of them. Then the second Gauss-Markov assumption is that the covariance of this is the identity times some constant variance sigma squared. However, in generalized least squared, we change that assumption to the covariance of epsilon given the inputs is some general positive definite covariance matrix omega. Now, let's examine the omega, specifically its relationship, or not its relationship, but what it's the significance of its eigenvalues and eigenvectors. So the directions in Rn, because this is a matrix, omega is in Rn by n. It's an n by n matrix. So the directions in Rn, along which the noise varies independently, right, is given by the eigenvectors of omega. And let me call those eigenvectors ui. The variances of the noise along these directions is given by the eigenvalues lambda I of omega. So let's write down a spectral decomposition of omega. So a spectral decomposition of a positive definite matrix looks like this. So matrix U times a diagonal matrix lambda times the same matrix U transposed. Now this matrix U is given by this matrix. The first column is the first eigenvector of omega, and then the second eigenvector is the second column down to the last eigenvector. So the columns of U are the orthonormal, these are orthonormal, eigenvectors are orthonormal, meaning they're orthogonal to each other, and also they're normalized so that they have unit length or unit size, unit length or size. So this matrix here is formed by the eigenvectors of omega. This matrix here is a diagonal matrix. It's this matrix here. So it's a diagonal matrix of the eigenvalues, and there are n of them, as long as there's no degeneracy of omega. So this is the matrix lambda 1, lambda 2 down to lambda n. Everything else is 0. So this is the eigen decomposition of omega. Now let's use this. Let's use it to write epsilon in the eigenbasis. And we'll see why this is the natural way to write the error. So we want to write epsilon in the eigenbasis, meaning we want to write epsilon as a linear combination of these ui's, I equals 1 to n. So some coefficient zi times ui. And those coefficients are given by the dot product of epsilon with the ith eigenvector. Or we can write a vector of all of these z1 down to zn as this matrix the matrix U, the columns of which are these, transpose times the vector epsilon. So let me explain a couple of things here. Why do we call this an eigenbasis? Well, what's the space we're working in? Rn. Now we have these vectors from I equals 1 up to n. They are all they're mutually orthogonal and they're normalized so that they have unit length. That part doesn't matter for this purpose here. They're mutually orthogonal. If they're mutually orthogonal, they are automatically linearly independent, right? Linear orthogonality implies linear independence, but not vice versa. So these ui from I equals 1 to n form a basis for Rn. We have n of them, right? We have n of them, exactly n, and they're mutually orthogonal. Therefore, they are linearly independent. Therefore, this is a basis. That means any vector in Rn, let me call it V, can be written as a linear combination of these ui's with some coefficients ai. Right? Now, this is what we've done with epsilon. We're writing it in the eigenbasis that comes from that covariance matrix. So these are the eigenvectors of the covariance matrix. Now, why is this the form of the coefficients, these zi's? Well, let's think about this. So let's take this expression here. So this is simply saying that epsilon is a linear combination of these, can be written as a linear combination of these, which it definitely can. So we've got the sum from I equals 1 up to n of zi ui. So let's pick one of these u's. Let's say uj, the jth one. Let's take the dot product of uj with epsilon. And therefore, we have to take for equality here, we have to take the dot product of this sum with uj. Right? Now, this can be taken inside. This is just a number. So this becomes the sum, I equals 1 up to n. So we've got zi, that's just a number. Then this transpose this, or the dot product of these two. Now, these are mutually orthogonal. So in this sum, this will be 0 because they're orthogonal. This is a dot product of these two. Well, that's going to be 0 unless I equals j, because we picked the jth one, right? So this will be zj. So only when I equals j will this be non-zero. And when I equals j, we'll get uj transpose uj. But these are orthonormal. They have unit length. So this, which is uj squared, the 2 norm of uj is equal to 1. So we get zj. So zj is uj transpose epsilon, which is the formula I have here. Okay. And we can write compactly the vector of all of these is the matrix U transpose epsilon. Now let's compute the covariance of this coordinate vector. Well, what will that be? Well, where does it come from? Well, what's the covariance of epsilon? That's omega, conditioned on phi. And what's z? Z is a linear transformation of epsilon. So the covariance of this linear transformation will be the covariance of epsilon times this matrix times the transpose of this matrix, U transpose transpose. But that's just U. And what's covariance of epsilon? It's omega. So we get U transpose, covariance of omega, which is omega, times U, right? Which is what? That's lambda, right? Why is that lambda? Well, let's remind ourselves. What is this lambda? Well, let me just do it from here. So we've got U transpose and then omega. The decomposition of that is U times lambda times U transpose. That's the eigen decomposition of omega. And that's multiplied by this final U here. But U, I should have mentioned, U is a unitary matrix. So U transpose is its inverse, right? And also, so therefore U transpose U is the identity matrix. So that's just the identity. And U transpose U, again here, It's the identity. So we're left with just this. So in the eigenbasis, what happens? This is why the eigenbasis is the natural basis in which to express the error. Because in that basis, if we write epsilon, in this basis, the ui's, the coefficients in that basis, the zi, are uncorrelated. This is a diagonal matrix. So on the off-diagonal terms are 0. That means these are mutually uncorrelated. And the variances of these zi are given by the elements of this, the diagonal entries of this. So this is the matrix lambda 1 to lambda n with zeros here. Right? So we get this situation. So in the eigenbasis, the noise decomposes into independent components with these variances given by the eigenvalues. So this is why writing the error in the eigenbasis is a natural thing to do. Okay. Now let's see what the whitening does using this eigenbasis. So we're going to transform. We're going to transform using a transformation. So before I said, what did I say? I said that we can use any square root of omega. So any square root is any matrix A that satisfies this. Now before we used a Cholesky decomposition, where this is a lower triangular matrix. And then our transformation, our whitening transformation was we transform y like this, and we transform epsilon like this, and we transform the design matrix using the same transformation, linear transformation. Now we can use any square root. We don't have to use this Cholesky decomposition. Another square root is given by our eigen decomposition. And what is that? Well, our eigen decomposition tells us that omega is equal to u times lambda times u transpose. Now we can define a square root from here, and that square root is u times lambda to the half times u transpose. Right? Now let me convince you. So let's do this times the transpose of itself, u lambda to the half u transpose. So first of all, let me explain what this lambda to the half is. Lambda, the matrix, is this, lambda n, zeros here, and so lambda to the half is the same matrix, but we just put these become square roots or powers to the half. Everything else remains 0. So this is still a diagonal matrix with this thing here. So what is this? Well, this is going to be u times lambda to the half times u transpose. Now we need to transpose this whole thing. So we're going to get u transpose transpose, which is u, times lambda to the half transpose. That's a diagonal matrix. We don't change it. We transpose it. So it remains as lambda to the half. And then the transpose of that. Right. Now, that's a unitary matrix, so that cancels. Lambda to the half times itself is lambda. So we get u times lambda times u transpose. So this is omega. So indeed, this is a square root of omega, another square root. And there are infinitely many square roots, right? They're not unique, but this is one of them, and Cholesky factor is another one. Now, if this is a square root, what's the inverse of this? Well, we can call this square root, we can call it omega to the half. So this, I'm labeling omega to the half is a square root of omega. So, and what's the inverse of this? Let me call that omega to the minus a half. It's the inverse of this. Well, it's going to be u. So we take the u transpose. So we want the inverse of this. U transpose inverse. But u transpose is the inverse of u. So u inverse inverse just gives us u. Right? That is u transpose inverse. But u inverse, u transpose is u inverse. So that takes us back to u. And then we've got the inverse of this, which is lambda to the minus a half. And then the inverse of this, which is the inverse of u. But the inverse of u is the transpose of u. So that gives us transpose of u. And this is, so this, if that's lambda to the half, then lambda to the minus half is this diagonal matrix with 1 over all of these. Right? Okay, so this is one Whitening transformation we can use. And let's apply this to epsilon. What do we get? Well, we get a new transformed error, epsilon tilde, as this linear transformation here. Now, what is, so we've got u times lambda to the minus a half times u transpose times epsilon. But u transpose epsilon is the coefficient vector of epsilon in the eigenbasis, which I call z. Okay, so now what is the what does this look like in the eigenbasis? What is the coefficient vector of this in the eigenbasis? Well, we apply the same transformation. The coefficient vector of this in the eigenbasis will be given by u transpose times epsilon tilde, which is what? It's u transpose times this thing here. But u is unitary, so u transpose u, lambda to the minus a half z, that cancels to give us the identity. It's just this, so we get this. And what is this? Well, so it's lambda to the minus a half. So let me write lambda 1 to the minus a half, meaning 1 over the square root lambda n to the minus a half. This times the coefficient vector of epsilon in the eigenbasis, z1 to zn. And this is nothing more than the vector z1 over lambda 1 to the minus to the half. Let me just write it like that, square root z2 over square root of lambda 2 down to zn over the square root of lambda n. So it's this vector here. So the ith coefficient of this is given by the ith coefficient of the original coefficient vector of epsilon in the eigenbasis divided by the square root of lambda I. So we're rescaling by this Whitening transformation, we're rescaling the eigenbasis representation by dividing by the variance in the direction, or square root of the variance into the direction ui, which is what this coefficient corresponds to. It's the coefficient in the direction ui. So let's see what this means in practice. Well, let's calculate the covariance of this new coefficient vector, the one that's been transformed by the Whitening transformation. Well, what is the transformation? Well, the transformation is, so z tilde is lambda to the minus a half times z. Now we calculated the covariance of z, given the design matrix, is equal to lambda. So the covariance of this transformation of z will be lambda, the covariance matrix of z, with lambda to the minus a half at the front, and the transpose of lambda to the minus a half. So the transpose of this. But this is a diagonal matrix. If we transpose it, we don't change it. So what we've got here is the inverse square root of lambda times this inverse square root. The whole thing will cancel. This is just the identity matrix. So the covariance of this Whitening transformed coefficient vector z in the eigenbasis is the identity matrix. So let's see what all of this means. Well, what is the objective? Let's first tie this into the objective. And this is the key thing, really, in all of this. Well, the objective is what? The objective is to minimize the Mahalanobis distance. And what is the Mahalanobis distance? It's y minus phi theta transpose omega minus 1 y minus phi theta, right? But y minus phi theta is epsilon. So what we're doing is we're minimizing this epsilon, omega to the minus 1 epsilon. So this is actually our objective. And this is the transformed, Whitening transformed epsilon dot product with itself. And what is it? Well, it's given by, so this was epsilon tilde times transpose dot product of that with itself. And what is that? Well, let's transpose this. We're going to get z transpose times this transpose, it's diagonal, so if we transpose it, we don't change it, times this transpose. That's times u times lambda to the minus a half times z. That's unitary, so that becomes the identity. That times that is lambda to the minus 1. So we get z transpose lambda to the minus 1 times z. Now what's lambda to the minus 1? That's just 1 over lambda 1 down to 1 over lambda n. So if we have a vector z, right, the transpose of it is this row vector here, so that's z. And then we have the column vector z here, right? So this will be equal to, it's just like a normal dot product. So if we got rid of this, that would just be a normal product. Dot product would be the sum from let me just get rid of that. Let me write it. Oh, I shouldn't have done that. So let me write that again. So z transpose lambda to the minus 1 times z will be just the same as a normal dot product, z transpose z, which would give us I equals 1 up to n, zi squared, except we divide each term by lambda I. So the objective becomes this, where we're weighting the errors according to these variances. So this is the transformed z. This is the Whitening transform z in the eigenbasis, zi tilde squared. Zi over square root of lambda I is zi tilde. And what we're doing is this, we're reweighting in the minimization, in the objective, we're reweighting the terms according to the size of the variance. So that's what the Whitening does. It rescales the coordinates of the eigenbasis according to their variance. So what is the effect of this? Let's think about it. Well, if lambda I is big, right, what does that suggest? It suggests we have a lot of uncertainty in the direction ui. Now, what does ui represent? This is not going to be for observations. This is going to be mixed for a mix of observations, right, corresponding to the direction ui. And if lambda I is big in that direction, in this eigen direction, that suggests we have a lot of uncertainty. So what does this do? It downweights that error, square error. It downweights the square error in the minimization if lambda I is big. If we have a lot of uncertainty, it says, okay, let's downweight this. We're not sure that this is a very accurate reading. On the other hand, if lambda I is small, that suggests we have low uncertainty, we have high confidence. So it doesn't downvote it in that case. It gives it more weight, right? So this is a totally natural thing to do, right? And you can see now by writing it in this way why precisely this generalized least square idea works. Okay, so let me leave that there, and then we will come back to this when we look at a special case, which is weighted least squares. Yeah, where we have a diagonal omega. Now, in the next part, so there's one more part actually. Let's actually show one last thing, which is that we have optimality. So let's apply our Whitening transformation. And what do we get? We get this system here in which the noise is white or spherical. And we know from Gauss-Markov that this, if we use OLS, is blue. So the OLS for this problem, the ordinary least square solution for this problem, is the best linear unbiased estimator. Now, this transformation is invertible. And so we conclude that generalized least squares is the best linear unbiased estimator for all errors with this covariance, omega. Okay. So we do indeed have optimality via the standard Gauss-Markov result. And we can actually directly prove it, but we don't need to. Because actually Gauss-Markov is more general. It's very general covariance matrix like this. But we can do it via the standard standard model with this covariance, which we've already proved in a previous video. Okay, so let me stop there, and then next time we will move on to feasible ways of implementing generalized least squares.